and charge separation in the photosynthetic reaction center. So Jennifer, floor is yours.
And the talk is recorded, just for, I need to inform everybody.
Okay, great. Let me see here. Can everyone see my screen?
Yes.
Okay, and I have
it's
a pointer.
perfect.
Okay, wonderful. All right, well, I'm really excited to be here today, and I'd like to really thank Thomas and Maxime for the kind invitation, and for putting together this great series that's keeping us all connected during this difficult time. I hope everyone's doing okay out there. So yes, today I'd like to tell you a bit about some of the work we've been doing to understand charge separation and coherence in photosynthetic reaction centers. Before I get into my talk, I'd like to alert you, in case you hadn't heard about this special issue in the Journal of Chemical Physics on coherent multidimensional spectroscopy. It would be great to get exciting contributions from everyone, and March 31st is the new deadline. So hope to see lots of great papers from all of you. Now, before I get into our work on reaction centers, I wanted to just take a moment to advertise some of the other things that we've been doing in the group that I won't have a chance to talk about today. So we heard a beautiful talk from Tobias Brixner in the first of these seminars, detailing some of his work in spatially resolved 2D electronic spectroscopy. My group's been working in this area as well, and we've been excited to be able to do this fluorescence detected 2D method on live purple bacteria. And there's a lot of interesting differences between the fluorescence detected and coherent detected spectra. And I've been working with Thomas McCord-Jensen and understanding some of that. And I'd like to also point out some papers. So the method that we've been using is a phase modulated approach that was developed, pioneered by Andy Marcus's group in Oregon. So if you're interested in this subject, here are some relevant references. Also, we've been applying, so I'm going to talk about our work in natural photosynthetic systems and specifically reaction centers today, but we've also been applying 2D spectroscopy more recently to look at charge generation in organic photovoltaic materials. And in particular, we've been doing some work combining 2D electronic spectroscopy and with infrared probing, so 2D EV methods as well, in a paper that I hope will be out soon. Okay, so I'm going to talk about first today some of the work we've been doing to understand coherence effects in bacterial reaction centers. And so this is really a beautiful model system for understanding photosynthetic systems in general. So purple bacteria, here I'm showing the basic architecture of the photosynthetic unit, where we have LH2 and LH1 antenna complexes that do the light gathering and then funnel the excitation into the reaction center where the initial charge separation events occur. So in the first part of the talk, I'm going to talk specifically about our observations of coherence in this bacterial reaction center. So here I'm showing the structure. This looks like it has twofold symmetry. However, the protein breaks that twofold symmetry, and electron transfer happens along the A branch, and leading to this initial charge separated state. So the electron moves on to the quinone here, but I'm going to talk about the events leading up to this initial charge separated state here. And there's been a lot of work done in the past in this system. Here are just a few relevant references, including a really nice review by Wolfgang Zinn. Now, my group actually started out looking at the photosystem 2 reaction center. I'm not going to talk about that today, but in that system, the structure is very similar, but unfortunately, every one of these pigments overlaps spectrally in this QY region. And so you have, we have a really difficult time figuring out what's happening in this system. In contrast, this bacterial reaction center has a lot more spectral separation. So here we're looking at what's called the special pair, which is a strongly coupled pair of bacterial chlorophyll pigments. And these give rise to an upper and lower exciton. Here's the bright lower exciton special pair state. these neighboring accessory bacteria chlorophyll give rise to the B band here in the center, and then the bacteria theophyton, termed H here, give rise to a nicely separated band. So, so here we have a much better chance of really following the events of both energy transfer and charge separation in the system. Also, these bacterial systems have a number of mutants available, and in particular, today I'm going to show you work where we've used a mutant that knocks out the quinone here, allowing us to use a kilohertz laser to study the initial charge separation events. Okay, so I'm going to play you a movie stepping through the waiting time, and just to orient you in our spectra. So here is the lower P special pair state, B and H, and so you'll see very rapidly cross peaks forming as we have rapid energy transfer between B and P, and H and B, and then eventually H and P as well. Okay, and you'll also notice oscillatory motion in this spectrum. I'll be focusing on trying to understand that today. Okay, so we have previously published work in PNAS on the kinetic analysis of this data set. And we used an approach of multi-excitation global analysis that was pioneered by Donatas Sigmontis's group for describing energy transfer in FMO. Here we extended that approach where basically we, with this system, we know pretty much what the excitonic model should look like, not exactly where the transitions are. What's unknown though are the signatures of the charge separated intermediates. So we sort of extended their multi-excitation global analysis approach and simultaneously fit with an exciton model, the linear spectra, and then also the 2D spectra. And we were able to use this to test models of charge separation. And just briefly, the sort of overall conclusions were that we could fit our data very nicely with a single charge separation pathway model. And so here I'm showing on the top row here the data, and then the model, the fit that we get to our data. So you can see that we can describe the majority of the spectroscopic features. And from this, we can extract the exciton states, their energies. Okay, and also of note here, so the upper P exciton state, the position of this has been debated in the literature, and it's observable in our 2D spectra, but you see really quite a weak cross peak here. And through our kinetic fitting, though, we were able to assign the position of this upper P exciton state. Okay, now, so I'm not going to talk about the charge separation mechanism in that. I'll refer you to our published work on that. I'd like to move on and talk about coherence in the system. And I'd like to point out this early work by Martin Voss and Jean-Louis Martin, where in the early 90s, they used pump probe spectroscopy and reported coherence in this bacterial reaction center system. And so they saw these beautiful oscillations in their pump probe data. And they noted that this happened on the same time scale as the primary charge separation event. They interpreted these oscillations as arising from excited state vibrational coherence. And they did wonder about whether the coincidence in time scale with charge separation might imply some kind of functional importance. Okay, fast forward to reports of coherence in 2D spectroscopy, starting with the work from Fleming and Engel on FMO in 2007, which of course gave rise to a lot of work in the field. I can't list it all here, but for people interested in learning more about that story and how our understanding of coherence and how it's manifest in 2D spectra has developed over the years, I'd refer you to some of these key papers, and in particular to a recent review paper in Science Advances by a number of us in the field. I wanted to point out a couple of early papers that looked at by my group and also Harold Kaufman's group, looking at laser dyes and how vibrational coherence modulates 2D data. And there's also been quite a bit of work reporting coherence in the Bacterial Reaction Center as well. I'll point you to some of the papers there. Okay, so one of the things that we've learned in our evolution of understanding of coherence with as observed by 2D spectroscopy is that it's very useful to do an additional Fourier transformation along the waiting time and get basically a 3D frequency cube of data, and then take a slice at a particular coherence frequency, omega-2, to study the distribution in 2 dimensions in order to gain insight into the physical origin of the coherence. Okay, so what we've done in the Bacterial Reaction Center, we looked also at bacterial chlorophyll A. And so here what I'm showing you is I have taken that frequency cube and integrated along omega-1 and omega-3. And so I'm showing you basically what frequencies oscillate during the waiting time. Okay, and so the red is the BRC, the yellow is the monomer, and you can see a good correspondence between the monomer and reaction center modes. The blue lines here are from fluorescence line narrowing and resonance Raman experiments. So above about 400 wave numbers, the frequencies match quite well. And interestingly, when we take our excitonic model, so the positions of exciton states that we derived from our kinetic fitting from our previously published work, if we look at that excitonic structure and then the dominant vibrational modes that we identified from the coherence data, here I'm showing those modes with the height of these bars representing the vibrational energy. And you can see that many of these modes seem to span the electronic energy gaps in the system. Okay, and so we are observing electronic vibrational resonances in the BRC. Okay, so I want to say a few words about double-sided Feynman diagrams and coherence maps. So just briefly, so of course here I'm going to, with my double-sided Feynman diagram, walk through the evolution of the density matrix as I interact with the system with my different pulses in my experiment. So here I'm just going to show a representative rephasing map to describe the kind of information that we're going to see in these coherence maps. All right, so my first pulse comes in and I excite a coherence between the ground state and some excited state B. And then during T1, I will evolve in that coherence time. And if I Fourier transform my signal with respect to omega-1, I will, of course, get my excitation frequency axis. Then my second interaction comes in, and now in this particular diagram, I have a coherence between states D and B. Okay, and that will evolve during waiting time T2. And it will oscillate at the difference frequency between omega D and omega B. Okay, then my third pulse comes in. In this case, in this particular case, now I'm in a coherence between D and in the ground state. Okay, and then I have my signal emitted. Now, of course, Fourier transform with respect to T3 then gives me my detection frequency axis, and I'll see a feature here for this particular diagram, which in a coherence map will oscillate at this difference frequency. Okay, so this is just to illustrate how we can look at the two-dimensional distribution in these coherence maps and get insight into what's happening in the system. So there's been a lot of nice work to detail what different models, what kind of signatures we expect in coherence maps. So particularly relevant to the discussion that I'm going to go into today is this displaced oscillator model for purely vibrational coherence. So here, if we map out the rephasing pathways, we get something that looks kind of like a chair pattern. And this has been detailed in these papers here. So if we look, so I'm going to show you the monomer coherence map. So this is data on bacterial chlorophyll A. And so you can see that we get this kind of chair structure that we expect smeared along these diagonal lines. So the different features are separated by the omega-2 frequency, in this case 572 wave numbers, but we see a number of prominent modes. And you don't see as much of the chair in this high frequency mode due to laser bandwidth limitations. Okay, but the point here is that these maps are consistent with the vibrational coherence signatures that we expect. Okay, so things get a lot more interesting when we look at the bacterial reaction center coherence maps. All right, and so here, just to orient you, so here I'm showing the linear absorption spectrum on the top. And so this is this upper P exciton state that we identified previously in our kinetic fitting. And interestingly, we see really very prominent in the coherence maps, very prominent features at this upper P exciton state. Okay, so even though it was barely visible in the 2D spectra themselves, in the coherence maps, it really lights up. Now, interestingly, we also see some other features here that are difficult to explain using these sort of simple models of purely vibrational or vibronic or electronic coherence. And I'm going to focus today on these 4 features here. And so just looking at these, so they show up at the excitation of the upper P and lower P exciton. But interestingly, the detection axis here, the features correlate with the roughly with the position of BA. Okay, so we're exciting P, but we're seeing detection at BA and BA plus a vibrational quantum. Okay, you can see features 2 and 4 as I go up in coherence frequency are separated by that vibrational quantum. Okay. So in order to describe these signatures using double-sided Feynman diagrams and correlating those with the coherence maps, basically in this waiting time, we considered the possibility of coherence transfer processes. So if after 2 interactions with the system, I find myself in a coherence, in this case BD, if I can from there transfer to some other coherence, so for example CA, and in that case, now when my 3rd pulse comes along, I may end up with my detection at quite a different frequency. Okay, and in the coherence map, I will see oscillations both at the difference frequency of the initial coherence as well as the new coherence. Okay, so so we worked with Thomas Monschall to develop basically the simplest model we could that would describe the coherence signatures that we see in the BRC. And so in order to develop this model, we found that the simplest model that could successfully describe all of these features was to include the strongly coupled special pair, as well as the neighboring BA pigment. Okay, and we also needed to include a vibration, one vibrational mode at a time on the bacterial chlorophyll BA pigment. Okay, and so we were able to reproduce all of the different maps for the different frequencies that we see, but we're including one mode at a time in this model. Okay, so in the collective state basis, we have collective states that look like this, and we find, I pointed out that we had quasi-resonances between electronic energy gaps and vibrations, and so, for example, this energy gap between the ground state and an electronic excitation on B is roughly bridged by, or frequency difference of the upper P exciton plus a vibration is in quasi-resonance with this. So taking that model, this coupled system, and diagonalizing the Hamiltonian, I get, of course, my eigenstates. And so I end up with mixed vibronic states that have the character of some mixture of electronic excitation in the special pair or on B, along with vibrations on B as well. So some mixture of those states. Okay, so here's our data. In this case, I'm showing the rephasing map for positive frequencies. In this case, the mode is 742 wave numbers. So you can see data on the left and simulation on the right. And so we are able to reproduce the majority of these features. And in doing so, we also could go along and look at the different pathways that contribute to each of these different signals. And so in doing that, we classified the types of coherence and coherence transfer processes into 4 main types, okay? And so here I'm showing a plot. If we take our map and divide it into these 6 regions, well, 8 really, then we can go in and look at all of the different pathways and see what types of coherence give rise to the different features in these coherence maps. Okay, so I'm going to walk you through what these different types are. So the first type of coherence that we found was basically describing decaying vibrational coherence residing, in this case, so in the ground or excited state of the B molecule. Okay, so here during the T2 time, this is one representative pathway. We have the electronic excitation on the lower P exciton and a vibrational coherence in the ground state of B. Okay, and this decays during T2 and gives rise to features located at these locations on the coherence map. Okay, and these are related to the type of coherences reported in other studies on FMO, for example, by Tawari and Jonas. Only here we're looking at excited state processes, so excited state absorption signals rather than ground state leach ones. Also related to the coherences reported by Christensen and coworkers. Again, though, looking at, in this case, a distinction is that we're looking at excited state absorption contributions. The second type of coherence, here in this case, we identify vibronic coherence shift. So initially we begin in the excited electronic state corresponding to B. And then during T2, we have energy transfer from B to the lower P exciton. Okay, and so this, there's basically a coherence transfer associated with this energy transfer process. And this has been previously identified in studies of the oxidized bacterial reaction center by Zygmontis and coworkers. And they called this energy transfer induced coherence shift and published a really nice paper in Science Advances detailing their observations. Okay, and these type 2 processes contribute to these signatures 5 and 6 in the coherence maps. Okay, type 3, in this case, we begin in an electronic coherence between B and, in this case, the lower P exciton. And then during T2, we have a coherence transfer where we're ending up with the coherence in the ground state of B. Okay, so this is related to ETICS, perhaps a little bit different, but some kind of electronic process here with coherence transfer ending in the ground state on B. And these signatures contribute to all 4 of these peaks that we see in our data. Okay, and then finally, type 4 coherence that we identified, we call this armchair coherence. And in this case, what we're beginning with is vibrational coherence on the ground state of B. So we're in the electronic excitation is on P+, but then due to energy transfer, rapid energy transfer from P+ to P-, we have a transfer of coherence, but we basically maintain this coherence on the ground state, sort of vibrational coherence on the ground state of B. And this is the type of signature that really enabled us to observe this weak P+ exciton. Okay, so this turns out to be quite handy. And I'll point out a couple of other papers, a study by Bakulin and coworkers on singlet fission, where they, with coherence maps, were able to identify a very weak transition in their data. Also recent work by Kevin Kavarich's group in 2D-IR studies, they were able to see a dark state using coherence maps and coherence transfer processes. Okay, I wanted to point out that we also, we did explore other models. And interestingly, if we put the vibration on one of the special pair molecules rather than on B, we get distinctly different pattern that does not reproduce our data at all. Okay, so we thought that was quite interesting as well. So to conclude that part of the talk, there are, we find that there are numerous electronic vibrational, we call them quasi-resonances. These are not exact resonances between vibrations and excitonic energy gaps in the BRC. The coherence maps that are very handy for revealing weak or hidden states. In this case, it was the upper p exciton in our study. And these coherence maps reveal non-secular coherence transfer processes. So those types 2, 3, and 4 correspond to non-secular processes that are typically ignored in modeling energy transfer in photosynthetic systems. So it's interesting that we have a way to observe these types of processes. And future work, from theoreticians and perhaps on simpler systems is needed to assess, possible functional relevance of both the resonances and these non-secular processes. Okay, so in the second part of the talk, I'd like to tell you about a different reaction center that we've been looking at. And so this system is the heliobacterial reaction center. And this is a really nice system. It's thought to be the most similar to the common ancestor of all photosynthetic reaction centers. And the one that we're studying is from this Heliobacterium majesticaldum. So this system, actually the crystal structure was just recently solved in 2017 by Kevin Redding and co-workers. And that has revived interest in this system. And recently there was an excitonic model that was published on the system. So here I'm showing the structure. So there are many more pigments than the bacterial reaction center. And this reaction center is actually a homodimer. Okay, so it is symmetric. Unlike the bacterial reaction center, the charge separation happens on both sides in this system. And the antenna, so there are a total of about 60 pigments. Primarily bacterial chlorophyll G and bacterial chlorophyll G prime. But interestingly, for the spectroscopist, there's also these chlorophyll A pigments. And prior to the resolution of the crystal structure, it wasn't really known where these were located. It's exciting that they're in the reaction center because that opens up some nice opportunities for studying the charge separation in this system. Okay, so we were interested in using 2D spectroscopy to answer the question of which pigment is acting as the primary electron acceptor in this system. So we know that the charge separation, much like in the bacterial reaction center, we will end up in a charge separated state like this, only on both sides. Here I'm showing a single side, but it is, as I mentioned, a homodimer. But the question is whether the charge separation proceeds like in the bacterial reaction center, where the charge separation begins between the special pair and the accessory bacterial chlorophyll, or whether the initial charge separation begins between A0, the chlorophyll A, and the accessory. So we wanted to ask that question. And this work was Dr. Yin Song led this study in my group. Okay, so here I'm showing the linear absorption spectrum of the system, and you can see, a very nice large separation between the chlorophyll A QY transition here and the rest of this crowded bacterial chlorophyll QY region. Okay. And after the publishing of the crystal structure, Kimura and co-workers developed an excitonic model for the system that they published. And so we were interested also in testing their excitonic model. So in order to do that, we took advantage of our laboratory for ultrafast multidimensional optical spectroscopy. So this we've developed in recent years with Kevin Kvarich's group, led by Dr. Yin Song. So those of you who are Harry Potter fans might appreciate the acronym here, LUMOS. These are some of the people who contributed to the developing of the lab. the basic lab layout. So we were inspired by the dual amplifier design of Peter Ham some time ago, where they have a single oscillator that's seeding 2 regenerative amplifiers. And then with those 2 regens, we have a host of downhill light sources that span the UV, the visible, and the mid-IR, so that we can do combination spectroscopies. And in order for this to be sort of an easy to use facility, we primarily use 2D in the pump probe geometry using pulse shapers. So for the 2D IR, we're using a phase tech shaper with the approach pioneered by the Zani group. And for the visible, we're using our approach that we developed using the Dazzler. Okay, so we're excited in this lab to be able to span, 2D IR, 2D visible, also starting to do some 2D UV and combination methods. And of course, with the dual amplifier design, we can span femtoseconds to milliseconds. So we published the design of this in reviews of scientific instruments recently, if you'd like some more detail. Okay, so taking this, in order to get some insight into the excitonic structure of the HbRC, what we're going to do is we're going to excite in the region where we specifically excite A0, the chlorophyll A. But we're also going to hit the vibronic shoulder here of the bacterial chlorophyll QY. Okay, so in this waiting time 0 spectrum, what you're seeing here, this strong diagonal peak corresponds to the ground state bleach of the A0 pigment. And this cross peak 1 region up here, this is going to give us insight into the excitonic structure of the reaction center. So although we have many antenna pigments contributing here as well, we expect if we take a slice along this A0 wavelength to get some insight into the excitonic structure. Let me just comment on this cross peak 2 region. So here we've actually, as I mentioned, excited into the antenna region. And so with this single experiment, we can see what's happening both following excitation of the antenna as well as direct excitation into the reaction center. Here I'm showing from the excitonic model of Kimura and co-workers, the positions of the various exciton states. Okay, so here are 2 corresponding to primarily excitation of or participation by A0, and then these are from the bacterial chlorophyll G and G prime pigments. If we take a slice along A0, so here we've been working in collaboration with Darius Abramovich's and his group, then what we can do is, so here I'm showing the blue is our experimental slice along the A0 excitation wavelength, and then simulations using the exciton model proposed by Kimura. So we were quite interested in seeing whether there was good agreement or not between the positions of the cross peaks that we observe in our data compared to the model. So you can see that there's not particularly good agreement in this cross peak region. Here, the composition of the exciton states is shown in these colored bars here. Okay, so we refined the model slightly. We found that if we shifted the accessory bacterial chlorophyll site energy by a relatively small amount, we could get considerably better agreement with these slice spectra. And so this work is ongoing with Darius's group. Okay, so moving on to look at the time evolution as charge separation proceeds in this system. So here I'm showing a number of spectra at different waiting times. This system, unfortunately, because it's more complicated, there are many more pigments than in the bacterial reaction center. We couldn't do the same kind of multi-excitation global analysis, but we can still take our 2D spectra as a function of waiting time and perform kinetic analysis. And in this case, we decided to borrow from some of the methods used in the transient absorption literature. So we first did some lifetime density analysis in order to get a picture of what different timescales were needed to describe the data and to motivate target models that we would then do global fitting of. Okay, so in this lifetime density analysis, we're going to look at different excitation frequencies. We're going to look at the various timescales present in the data. Okay, and so we get a map that shows us as a function of detection wavelength the various lifetimes present in this kinetic data set. So here I'm showing the lifetime density map for excitation of the chlorophyll A pigments. And so some of the features that we see, so we see some very rapid initial energy transfer dynamics. And interestingly, we also see at a couple of different timescales at 1.7 and 230 picoseconds, some here in this region, this is the bacterial chlorophyll QX region, and we see sort of a stark type of line shape here. If I take a slice through, you can see that more clearly here. On these timescales, this derivative-like feature associated with in the bacterial chlorophyll QX, consistent with charge separation occurring. Okay, so we took these timescales as indicating charge separation timescales, and then used this analysis. We also did the analysis upon excitation of the antenna as well, and used that to form some target models. And then we did a global fit to those target models, where basically from the global target analysis, we get time-dependent concentrations here corresponding to various species-associated spectrum. Okay, and I'm not going to have time to go in detail through all of the spectra that we get out, but the punchline is that we were able to test quite a few different global target models, and this one in particular very nicely describes our data. And what we find significantly is that independent of whether we excite directly into the reaction center excitons or the antenna, we find that this model that has a single charge separation intermediate is consistent with the data. Okay, so this here I'm showing the species associated spectrum for this charge separation intermediate, and we see a ground state bleach of A0, and also this electrochromic shift associated with charge separation, and features in the bacterial chlorophyll QY region that indicate delocalization of the whole. So these features are consistent with this charge separated intermediate, and this intermediate is present regardless of whether we excite the antenna or the reaction center directly. And so this gives us good indication that A0 is the primary electron acceptor. So here, just to summarize this last part of the talk, so we've been able to refine the Kimura exciton model of the HbRC, and we've been able to also combine lifetime density analysis and global target analysis to show that independent of where the excitation occurs, we reach this common charge separation intermediate prior to the final charge separated state. And the A0 is this primary electron acceptor. Interestingly, we think that this delocalization that we saw may be important for limiting charge recombination, and may also be important in other reaction centers. So with that, I'd like to acknowledge my group. So the people in purple here contributed to the bacterial reaction center work, and the people in cyan contributed to the HbRC work. And I'd like to thank you for your attention, and also just to mention that we're always looking for great team members. So if anyone is interested in a postdoc position, please contact me, and I'd love to take your questions. Thank you.
Thank you very much, Jennifer. So if anybody have a question, please just raise your hand in the on the bottom of the screen, then we can promote you to panelist, or you can write a question in a question or answer or in the chat, but it's easier if you just raise your hand.
Are you sure that this raise hand option is here, Thomas? Because that's a webinar.
Oh yeah, I have it.
Oh,
We
wow.
had it last time as well.
Okay, good. Like you, because I don't see that, but that's fine.
I think if you press alternate and Y, it also will raise a hand.
I didn't understand the question. Donatus have a question.
Yeah, then others, you can talk. Then others?
Does he have to be a panelist to?
Yes, I think that
Yeah,
Thomas
but
just promoted.
he should be a panelist, but he was muted.
Yeah, the nuts is here. The nuts, we can hear you. Okay, maybe, yeah, John, I saw that you said that you have a question. Maybe you will ask the question now, and then Donatus will come if he comes.
Okay, I'm trying to speak. Can you hear me?
Yes.
Yes.
Oh, good. Beautiful talk, Jennifer. I really enjoyed that. I wanted to explore this idea of secular and non-secular because, you know, in the studies that we did with these rhodium dicarbonyls, we also saw this coherence transfer, but if we would only be able to model it if it was an instantaneous excitation. But if we included the fact that the lasers were on for a picosecond, all of this disappeared because of the secular approximation.
Mm-hmm.
So the problem, I think, was that you have to store phase information someplace when the coherence transfer takes place, which I always assumed was in the bath. Now, if I understand what you're saying, you also have these non-secular effects. And what you're saying is that the memory of the phase is being stored in the vibrational modes. Is that the way that you're thinking about it?
Yes. Yes, I think so.
Okay. Yeah. Beautiful work. Thank you.
Thank you.
Okay.
Now we can see
Donatus?
Donatus.
I can
cannot
hear
hear
you,
you.
Donatus, but I cannot. I can see you, but I cannot hear you.
Maybe
No.
maybe type the question in the chat.
Yeah, perhaps. We can hear you. Type it. Okay, more questions?
Maybe I can ask a question while we're waiting for Donatus. So you're talking about these coherence transfer taking place. Do you have an idea of how long time, what the time scale is for that transfer?
So yeah, so this is a good question. You know, we have done a bit of analysis using sort of sliding Fourier window to try to see that. But you know, the energy transfer that happens in the system is pretty fast, and we think that these processes are correlated with energy transfer events. So I think, you know, a lot of this is happening likely in the first 100 femtoseconds or a few hundred femtoseconds. Yeah. So in the modeling, we consider the coherence transfer happening during the waiting time. I know that in the 2DIR community, people have also considered coherence transfer occurring in T1 as well.
Okay.
Okay, one more try with Donatas.
Can you hear me now?
Yes.
Yay.
Yes, perfect. So I cannot hear you, Phil. Say something. I just want to test if I can hear you.
Can you hear us?
Okay, now I can hear you. Oh,
Okay.
sorry for always. So very nice work, Jennifer, as always. So I was kind of mesmerized by these, let's say, the purple bacteria reaction center interpretation of coherent signals. It's a rather complicated, complex scheme what you came up with Tomasz. And I was thinking, have you considered applying some polarization control schemes to basically filter out most of the signals, and which would actually help you to filter out the most interesting signals which have some vibronic mixing?
Yes.
Yeah.
Yeah, so we definitely would love to do that. I know that your group, of course, has done beautiful work with that. And so Cameron in my group is currently working on that, among other things. We, our experiments are primarily using the Dazzler, and the Dazzler, so, in your experiments, you're changing the polarization between, of both pumps. And we can't easily do that with the Dazzler. It is possible with the second Dazzler. Pat Body has shown that. But actually, our version of the experiment where we combine boxcars with the Dazzler, it is possible to do polarization control there. So we are setting that up, but we don't have results to show on that yet. But yeah, that would be great. We definitely plan to do that.
Okay, thank you.
So there's also a question from Martin Vos.
Oh, great.
Hi, Jennifer. Very nice talk as usual.
Thank you. Nice to see
I was
you.
very impressed by to see that you dared to look into the heliobacterial reaction center, because it's extremely complex. It's also very nice to see that it's actually much more complicated as we thought about it before we even had to structure it all. So if I understand well, your model is now that on the tens of picosecond timescales, what we usually thought of being at the charge separation timescale, it's actually more equilibration to lower lying pigments or something like that. Is that correct?
Well, so let me go back. Are you okay? Are you still seeing my? I'm not sure why I don't seem to have control over.
I see your acknowledgements.
Okay. Yes. Okay. Do you see now? Whoops. Okay. All right. So actually, what we do see is this intermediate charge separated state that seems to form quite rapidly, but there is still, a slower process as well to this final charge separated state.
Okay. So that's okay. So what you call the primary acceptor is actually is not really the first one, or at least the intermediate is on the oxidized side. Now,
Yeah. So this first step is very fast, and then there's the slower secondary step.
Okay. And then would you foresee to also look at this at lower temperature, because where there things should be a bit more?
I should have mentioned this is at 77 K.
Okay, that makes sense.
Yeah, I forgot to say that. Thanks for. Yeah. Okay. So what are your thoughts about this? Do you are you surprised at how fast this is, or?
Well, then it makes it in the sense that these lower exciton states are really traps, because that's why I'm a bit surprised to see that at room temperature, but because then you don't see them. Okay, well, it's a lot of new information. Should be very interesting to see it finally.
Okay,
Thank you.
thanks.
Okay, then I understand that there are no questions anymore. So I am stopping the recording of this talk.